Give it a second, we'll have.
Yeah, okay, great, fantastic. Well, thank you everybody for joining us at KCL. And we're going to kick off the autumn following from the wonderful talk that Marion gave last week for the RIOT Club in the Netherlands. And Marion's talk will be uploaded to our OSF and our YouTube channel in good time. We're just working on the recording for that. On my screen now, you may be able to see the upcoming talks for the autumn period, and we're very pleased to welcome on board a new site, Exeter RIOT Science Club, and you'll be hearing much more of those in autumn and in the new year as well. Also, one other announcement as well. Some of you will already know that I am no longer the UKRN network lead at King's. I'm glad to say that we have a wonderful replacement, Alexandra Lutrescu. Hopefully I haven't butchered your name, Alexandra. I've sort of quickly danced over your last name, so I always find it difficult to pronounce names.
That was good, thank you.
Oh, is it? Okay, perfect. That. You're not hallucinating. Alexandra is actually in the background, so thanks for that, Alex. And do be sure to follow her. But anyway, no more ado. Today we're joined by David Colquhoun, another name which I hopefully have pronounced correctly. David is a pharmacologist notable for his insights into biophysics of drug receptor interactions of single ion channels. And he was elected a Fellow of the Royal Society in 1985, was awarded the Humboldt Prize in 1990 and made Honorary Fellow of UCL in 2004. Colquhoun joined the pharmacology department at UCL in 1964, and apart from 9 years, has remained there ever since. It's quite an achievement. He can of course be found on Twitter at David_Colquhoun, and please do visit his wonderful website if you haven't done so already, which is DC's Improbable Science, and we can provide a link in the Q&A message board, where he writes critically about pseudoscience and alternative medicine. Before I hand the keys over to David, please know that the Q&A message board can be found at the side of the screen. It will remain live throughout David's talk, and what we will do is we will compile all of the questions and feed them to David at the end of his talk. David has very kindly said that he's more than happy to stay on until the bitter end, so please do keep your questions coming. Just to help also the co-producers, the little elves in the background, just upvote any questions that are kind of similar to what you would ask, so that we don't get a deluge of very duplicated questions. Okay, so David, you've already started, you're one step ahead, so I'll stop nattering on and I'll pass it over to you. Thank you again, David, for your time.
Okay, thank you. This topic of conversation is something which I've sort of taken up in my semi-retirement as a way of keeping me off the streets, but it's turned out to be very interesting, I think.
Today I speak to you of war. A war that has pitted statistician against statistician for nearly 100 years. A mathematical conflict that has recently come to the attention of the normal people. And these normal people look on in fear, in horror, but mostly in confusion because they have no idea why we're fighting.
Okay, so that sums up a lot of what's been going on. The problem is that there is near unanimity among statisticians that p-values don't tell you what you need to know, but statisticians themselves haven't been able to agree on a better way of doing things. The talk is about the probability that if we claim to have made a discovery, we'll be wrong. This is what people very frequently want to know. And that is not the p-value. you want to know the probability that you'll make a fool of yourself by claiming that an effect is real, when in fact it's nothing but chance. Just to be clear, what I'm talking about is how you interpret the result of a single unbiased experiment. Unbiased in the sense that the experiment is randomized and all the assumptions made in the analysis are exactly true. Of course, in real life, false positives can arise in any number of other ways. Faults in the randomization and blinding, incorrect assumptions in the analysis, multiple comparisons, p-hacking, and all of these things are going to make the risk of false positives even worse. So in a sense, what I'm talking about is your minimum risk of making a false positive, even if everything else were perfect. And this really comes before all the others. So what I'll be the conclusion of the talk will be that if you observe a p-value close to 0.05 and conclude that you discover something, then you've discovered something, then the chance that you'll be wrong is not 5%, but it's, well, somewhere between 20 and 30%, depending on the exact assumptions you make. And if the hypothesis was an implausible one, to start with, the false positive risk will be much higher. There's nothing new about this at all. This was written by a psychologist in 1966. The major point of this paper is that the test of significance does not provide the information concerning phenomena characteristically attributed to it, and that a great deal of mischief has been associated with its use. And he goes on to say, this is already well known, but if so, it's not well known by many journal editors or indeed many users. So let's start by defining the p-value. An awful lot of people can't do this, but even if you can do it, it's surprisingly difficult to interpret it. I consider it in the context of comparing two independent samples to make it a bit more concrete. So the p-value is defined thus: if there were actually no effect, for example, if the true means for the two samples were equal, so the difference was 0, then the probability of observing a value for the difference between means which was equal to or greater than that actually observed is called the p-value. Now, there's at least 4 things wrong with that when you think about it. It sounds very plausible, but it's not. If there were actually no effect, first of all, this implies that the denominator for the probability is the number of cases in which there is no effect, and this is not known. Or greater than. Why on earth should we be interested in values that haven't been observed? We know what the effect size that was observed was, so why should we be interested in values that are greater than that, which haven't been observed? Another thing wrong with it is it doesn't compare the hypothesis of no effect with anything else. It's put well by Selke et al. In 2001. Knowing that the data are rare when there is no true difference, that's what the p-value tells you, is of little use unless one determines whether or not they are also rare when there is a true difference. You've got, in order to understand things properly, to have not only the null hypothesis, but an alternative hypothesis. And fourthly, the definition makes the error of the transposed conditional. That sounds a bit fancy, but it's very easy to say what it is. In this slide, read the vertical bar as given. So the probability that you have 4 legs given that you're a cow is high, but the probability that you're a cow given that you've got 4 legs is quite low. Many animals that have 4 legs that aren't cows. take a legal example, the probability of getting the evidence, given that you're guilty, may be known, isn't of course, but that's the sort of thing you can hope to get, but it's not what you want. What you want is the probability that you're guilty given the evidence. The probability that you're Catholic, given that you're the Pope, is probably very high, unless the Pope is one of those unbelievers that hasn't admitted it. But the probability that you're a Pope, given that you're a Catholic, is very low. Notice that the thing after the vertical bar forms the denominator. This looks among all popes, and this looks among all Catholics. So now, to the nub of the matter, the probability of the observations, given that the null hypothesis is true, is the p-value, but it's not what you want. What you want is the probability that the null hypothesis is true, given the observations. The first statement is a deductive process. The second process is inductive, and that's where the problems lie. So these probabilities can be hugely different, and transposing the conditional simply doesn't work. The false positive risk avoids these problems. If you define the false positive risk as follows: if you declare a result to be significant based on a p-value after doing a single unbiased experiment, the false probability risk is the probability that your result is in fact a false positive. It's the probability that a positive result is a false positive. That's, I maintain, is what you need to know. The probability, the problem is that in order to get it, you need Bayes' theorem. And as soon as that's mentioned, contention immediately follows. This is the only equation I'll put in, and it's not a real one, it's just in words. Suppose we call the null hypothesis H0 and the alternative hypothesis H1. H1, H0 can be the true effect size is 0, and H1 can be the hypothesis that there's a real effect, not just chance. So the odds on H1 after you've done the experiment are equal to the likelihood ratio times the odds on there being a real effect before the experiment. In general, it would be a Bayes factor rather than a likelihood ratio, but that's the complication that my assumptions get round, and we can use the likelihood ratio, which is a much simpler thing. What the likelihood ratio represents is the evidence supplied by the experiment. It's what converts the prior odds to the posterior odds in the language of Bayes' theorem. And the likelihood ratio is a purely deductive quantity and therefore uncontentious. It's the probability of the observations if there's a real effect divided by the probability of the observations if there's no effect. Notice a simplification you can make. If the prior odds, this bit, are 1, then the posterior odds are simply equal to the likelihood ratio. Prior odds of 1 means that it's equally likely before the experiment that there was an effect and that there's no effect. So that's probably the nearest you can get to declaring equipoise. Now, I wrote a statistics textbook in 1971, which is by and large stood the test of time. But the one thing I got completely wrong was the limitations of p-values. And I came to see these, like many other people, through thinking about screening tests. Of course, screening tests are very much in the news at the moment because of COVID. And this is an illustration of the problems they pose, which is now quite commonplace, but I'll just go through it quickly. Suppose you test 10,000 people and that 1 in 100 of those people have the condition, say COVID, and 99% don't. So the prevalence in the population you're testing is 1 in 100. So you have 100 people with the condition and 9,900 who don't. If the specificity of the test is 95%, that means you get 5% false positives. This is very much like a null hypothesis test of significance. But you can't get the answer without considering the alternative hypothesis, which null hypothesis significance tests don't do. If you've got 1%, I've got 100 people who have the condition. If the sensitivity of the test is 80%, that's like the power of a significance test, then you get 80 true positive negatives. So the total number of positive tests is 80 plus 495, and the proportion of tests that are false is 495 false positives on the total number of positives, which is 86%. 86% false positives is pretty disastrous, and it's not 5%. It's not. Most people are quite surprised by that when they first come across it. Now, we can do something similar for significance tests, though the parallel, as I'll explain, is not exact. Suppose we do 1,000 tests, and in 10% of them there's a real effect, and in 90% of them there is no effect. If the significance level, so-called, is 0.05, then we get 5 false positive tests, which is 45 false positives. But, and that's as far as you can go with a null hypothesis significance test. You can't tell what's going on unless you consider the other arm. If the power is 80%, then we get 80 true positive tests and 20 false negative tests. So the total number of positive tests is 80 plus 45, and the false discovery risk is the number of false positives divided by the total number of positives, which is 36%. So the p-value is not the false positive risk. The type 1 error rate is not the false positive risk, but the difference lies not in the numerator, it lies in the denominator. In that example of the 900 tests in which the null hypothesis was true, there were 45 false positives. And so look at it from the classical point of view, the false positive risk would turn out to be 45 over 900, which is 0.05, but that's not what you want. What you want is the total number of false positives divided by the total number of positives, which is 0.36. As I said, the false positive risk in that case is 36%, not 5%. But now we have to come to a slightly subtle complication, which has been around since the 1930s, and it was made very explicit by Dennis Lindley in the 1950s, yet it's unknown to most people, which is very weird. The point is that there are 2 different ways in which we can calculate the likelihood ratio, and therefore 2 different ways of getting the false positive risk. A lot of writers, including Ioannidis and Rachholder and many others, use the P less than approach. That's what that tree diagram gives you. But it is not what is appropriate for interpretation of a single experiment. It underestimates the false positive risk. What we need is the P equals approach, and I'll try and explain that now. Suppose we do a test and we observe that P equals 0.047. Then all we are interested in is how tests behave that come out with P equals 0.047. We aren't interested in any other different P value. That P value is now part of the data. That tree diagram approach I've just been through gave a false positive risk of only 6%. If you assume that the prevalence of true effects was 0.5 prior odds of 1. 6% isn't much different from 5%, so it might seem okay. But the tree diagram approach, which although is very simple, asks the wrong questions. It looks at all tests that gives P equal to or less than 0.05, the P less than case. If we observe P equals 0.047, then we should look only at tests that give P equals 0.047, rather than looking at all tests which give P equal to or less than 0.05. If we're doing it with simulations, of course, as in my 2014 paper, then you can't expect any test to give exactly 0.047, but what you can do is look at all the tests that come out with P in a narrow band around there, say between 0.045 and 0.05. And this approach gives a way of looking at the problem. It gives a different answer from the tree diagram approach. If you look only at tests that give P equals P values between 0.045 and 0.05, the false positive risk turns out to be not 6%, but at least 26%. I say at least because that assumes a prior probability of there being a real effect of 50-50.
Here are the top search results.
Oh, bloody hell. Shut up, Google. If only 10% of the experiments had a real effect, a prior of 0.1 in the tree diagram, this arises to a disastrous 76% of false positives. That really is pretty disastrous. Now, of course, the problem is you don't know this prior probability. I'm going to skip this slide for speed. It just goes through the actual numbers that I got in the 2014 simulation paper. Now, the problem, as always with Bayes' theorem, is that there exists an infinite number of answers. My approach is certainly not unique. No approach is unique when it comes to Bayes. In fact, not everyone agrees with this, but it is one of the simplest approaches. What I do is look at the likelihood ratio, that is to say, the relative probabilities of observing the data given two different hypotheses. One hypothesis is there's a zero effect, that's the null hypothesis, and the other hypothesis is that there's a real effect of the observed size. That's a maximum likelihood estimate of the real effect size. Notice that we are not saying that the effect is exactly zero, but rather we are asking whether a zero effect explains the observations better than the real effect. Now, this amounts to putting a lump of probability on there being a zero effect. If you put a prior probability of 0.5 for there being a zero effect, in other words, the prior odds are 1, that's regarded by some people as being over-skeptical, though others might regard 50-50 chance of the hypothesis being correct as high, given that most bright ideas turn out to be wrong. Certainly if you were screening 1,000 drugs, congeneric drugs, you'd be very lucky if 10% of them were effective. So what I can say, and this is given some substance in some of the papers I've written, that if you are willing to test a point null, in other words, put a lump of probability on the null hypothesis, then there are several methods of doing that, and they all give similar results to mine within a factor of 2 or so at least. This tweet sums it up. At least Bayesians attempt to find an approximate answer to the right question instead of struggling to interpret an exact answer to the wrong question, that being the p-value. Okay, now some actual results. First, the false positive risk as a function of the observed p-value. This slide is designed to show the difference between the p equals and the p less than cases. The top row shows what you get with a prior probability of 0.1. The bottom row shows the prior probability of 0.5. False positive risk plotted against the p-value. In each diagram, the dashed red line is the line of equality. That's where the points would lie if the p-value were the same as the false positive risk. And you can see that in every case, the blue lines, the false positive risk, is greater than the p-value. For a prior probability of 0.5, then the false positive risk is about 26%, for p equals 0.05. So from now on, I shall use only the p equals calculation, because that's clearly to test of significance. Now, another set of graphs for the false positive risk as a function of the observed p-value, but this time we'll vary the number in each sample. These are all for comparing two independent samples. So we have curves. Let's just concentrate on this log-log plot for a prior of 0.5. The curves are red for n equals 4, green for n equals 8, blue for n equals 16. The top row is for an implausible hypothesis with a prior of 0.1, is for a prior of 0.5. The power this corresponds to for n equals 4 is 22%, for n equals 8 is 46%, and for n equals 16, that's the blue one, it is 46%. Sorry, n equals 16, it's 78% the power. Now you can see these behave in a slightly curious way. For most of the range, it's what you'd expect. N equals 4, it gives you a higher false positive risk than n equals 8, and a higher and still higher than for n equals 16, the blue line. So they behave in an odd way around 0.05. They actually begin to cross. But the point is that in every case, they're above the line of equality. So the false positive risk is much bigger than the p-value in any circumstance. The really interesting one. When I first did the simulation study, I was challenged by the fact that the false positive risk actually becomes 1 if the experiment is a very powerful one. That seems a bit odd. This is a false positive FPR 50, which is what I mean by the false positive risk for prior odds of 1, or a 50-50 chance of there being a real effect or not a real effect. Let's just concentrate on the p equals 0.05 curve. And because the number per sample is changing, the power changes throughout the curve. For example, on this p equals 0.05 curve, for n equals 4, that's the lowest one, power is 0.22, but if you go to the other end of the curve, n equals 64, the power is 99.99%, something not achieved very often in practice. But how is it that p equals 0.05 can give you a false positive risk which approaches 100%? Even with p equals 0.01, it'll eventually approach a false positive risk of 0.001. Same with the other p-values, though it does so later, more slowly. In fact, this has been known for donkey's years. It's called the Jeffreys-Lindley paradox, though there's nothing paradoxical about it. The point is that if the power is 99%, then you expect almost every p-value to be very low. Everything is detected if you have a high power like that. And in fact, it would be very rare with that very high power, very rare to get a value as big as 0.05. Almost every p-value would be much less than 0.05. And that's why p equals 0.05 would, in that case, provide strong evidence for the null hypothesis. Even p equals 0.01 would provide strong evidence, because almost every p-value with that high power would be much less than 0.01. And this is a direct consequence of using the p equals definition, which I think is what one ought to do. In fact, it makes absolute sense, that Jeffreys-Lindley phenomenon, because in the reasons I've just explained. Now let's consider an actual practical example. This is a study of transcranial electromagnetic stimulation published in Science magazine, therefore a bit suspect to begin with. And it concluded that an improved associative memory performance was produced by transcranial electromagnetic stimulation. P equals 0.043. Well, in order to find out how many the sample size were, I had to dig right into the supplementary material. It was only 8, but nonetheless, let's assume that it had an adequate power and see what we make of it. In fact, it wasn't done in a proper parallel group way. It was done as before and after the stimulation and sham stimulation, and it produces one lousy asterisk. In fact, most of the paper was about functional magnetic resonance imaging. This was only mentioned as a subsection of figure 1, but it was what was tweeted out because it sounds more dramatic than other things, and it got a vast number of retweets. Now, according to my calculations, 0.043, p equals 0.043 means there's at least a 23% chance that it's a false positive. So how better might we express this, the result of this experiment? We could say that the increase in memory performance was 1.88 plus or minus 0.85, which is, you have to give the effect size. You can also give the confidence interval, 0.055 to 3.7. That's the extra words which are recalled on a baseline of about 10. So it's not a very big effect in the first place. and those give p equals 0.043. This implies a false positive risk, i.e. the probability that the results occurred by chance only, of at least 18%. That makes the result no more than suggestive. There's several other ways you can put the same idea. I don't like them as much. You could say that the increase in performance gave p equals 0.043, and in order to reduce the false positive risk to 0.05, it would be necessary to assume that the prior probability of there being a real effect was 81%. You'd have to be almost certain that there was a real effect before you did the experiment, before that result became convincing. Since there's no independent evidence that that's true, so the result is no more than suggestive. Or you could put it this way: the increase in performance gave p equals 0.043. In order to reduce the false positive risk to 0.05, it would have been necessary to observe p equals 0.0043. So the result is no more than suggestive. The reason I now prefer the first of these possibilities is because the other two involve an sort of implicit threshold of 0.05 for the false positive risk, and that's just as daft as assuming a threshold of 0.05 for the p-value. You can calculate these very easily with our web calculator. The input panel looks like this. There's three options. If you want to calculate the false positive risk for value and prior, we can put in the observed p-value 0.049, the prior probability of a real effect 0.5, the effect size, normalized effect size, 1 standard deviation number in each sample, and the output panel updates itself automatically. We see that the false positive risk for the p equals case is 2.6, and the likelihood ratio is 2.8. I'll come back to that in a minute. This sort of table can be very quickly calculated using that calculator or using the R programs which are provided with the papers. If we observe p equals 0.05, then it implies all the other things on this line. The prior probability that you need to postulate to get a 5% false positive risk would be 87%. You'd have to be almost 90% sure that there was a real effect before the experiment in order to get a 5% false positive risk. The likelihood ratio comes out to be about 3, and what that means is that your observations would be about 3 times more likely if there was a real effect than if there was no effect. 3 to 1 is very low odds compared with the 19 to 1 odds, which you might incorrectly infer from p equals 0.05. Positive risk for a prior of 0.5, the sort of default value, which I call the FPR 50, would be 27% when you observe p equals 0.05. In fact, these are just directly related to each other, 1 minus 2.8 over 0.27. So since the likelihood ratio is a purely deductive quantity, you can regard this as just being a transformation of the likelihood ratio, and regard this as also a purely deductive quantity, though in order to interpret it as a probability, a posterior probability, then you do have to go into Bayes' theorem. Risk was only 0. If the prior probability of a real effect was only 0.1, then that would correspond to a 76% false positive risk when you'd observe p equals 0.05. If we go to the other extreme, when we observe p equals 0.001, the likelihood ratio is 100, not 1,000, notice, but 100, and the false positive risk could be 1%. That sounds pretty good. Though, if it was an implausible hypothesis with only a 10% prior chance of being true, then the false positive risk would even then be above 5. It would be 8%, even when you observe p equals 0.001. In fact, to get this down to 0.05, you'd have to observe p equals 0.00043, and that's good food for thought. So, what should you do to prevent making a fool of yourself? Well, first of all, never use the words significant or non-significant, and don't use those pesky asterisks, please. It makes no sense to have a magic cutoff. Just give the p-value. Don't use plain bar graphs. Show the data as a series of dots. Always remember that it's a fundamental assumption of all significance tests that the treatments are randomized. When this isn't the case, that you can't expect an accurate result from a test. So I think you should still state the p-value and an estimate of the effect size with confidence intervals, but be aware that this tells you nothing very direct about the false positive risk. The p-value should be accompanied by an indication of the likely false positive risk. It won't be exact, but it doesn't really need to be. It does answer the right question. You can, for example, specify the FPR50, the false positive risk, based on a prior probability of 0.5. That's really just a more comprehensible way of specifying the likelihood ratio. And you can use other methods, but they all involve an implicit threshold of 0.05 for the false positive risk, which isn't desirable. So p equals 0.04 doesn't mean you discovered something. It means might be worth another look. In fact, even p equals 0.005 can, under some circumstances, be more compatible with the null hypothesis than with there being a real effect. So this doesn't leave Fisher looking very good. Robert Matthews said the plain fact is that 70 years ago, Ronald Fisher gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. Though in fact, it's not quite fair to blame R.A. Fisher, because he himself described a low standard of significance as the 5% point. So there are some papers I've written about it. This is where to go if you want up-to-date links. The web calculator, for example, the publish link, doesn't work very well anymore, thanks to a cock-up by UCL, but you can find the latest links to ones that do on onemol.org.uk. That's our single molecule site. But there's a tab there for papers about p-values, which link to everything and is up to date. Okay, that's it, folks.
Wonderful. Thank you very much, David. And thank you, everybody, for attending. This is our highest turnout to date, and it's a wonderful way to start the school year, if you like. We have questions already on the Q&A message board. Everybody else, if you can keep them coming in. As I say, David has kindly offered to stay until the bitter end answering people's questions, so take advantage of this. I'll just go in order from first come, first serve, but if anybody has a question they see on the message board that they would like answered, just upvote it with the thumbs up. Okay, so this is quite a lengthy one, David. If you want to, you can just sit back and let me read it out to you, or you can read it as well, just so that you properly understand it. But I'll just read it aloud for people as well who have visual difficulties. So there are lots of competing ideas about how best to deal with the issue of statistical testing. For the non-statistician, it is very hard to evaluate them and decide on what is the best approach. Is there any empirical evidence about what works best in practice? For example, training people to do analysis in different ways and then getting them to analyse data with known characteristics. If not, why not? And if it feels like we wouldn't rely so heavily on theory in, e.g., drug development, so why do we in stats? So that was quite a mouthful. I can go over it again, but did you catch the sort of gist of the question there?
Yes, more or less.
Okay.
I mean, why do we rely on theory in statistics? Because we might as well say, why do we rely on theory in mathematics? That's what it is. And you have concrete theories and concrete postulates, which is you don't have in drug testing. That's just empirical. So that's easy to say. What was the first bit of it again?
So yeah, so the first part was, is there any empirical evidence about what works best in practice? So for example, training people to do analysis in different ways and then getting them to analyze data with known characteristics. And if not, why not?
Well, why not? Because you never actually know, unless you're doing simulations, whether what the answer should be. And so so no, it's not known which works best in practice. Mm. I think you can rely on the fact that a lot of the alternative methods give similar answers. That's why I felt justified in using a rather simple assumptions for mine, because they're easier to understand and the answers you get don't differ greatly from much more complicated methods. I think in my 2019 paper or was it the 2017, there's a comparison of 3 different methods, all of which assume that it's reasonable to test a point null hypothesis, one that says that the treatment effect is exactly 0. But given that assumption, all the alternative methods give similar answers with a factor of 2 or so, and a factor of 2 is all you need. You know, it doesn't matter if it's 26% or 52% or 13%. The conclusions in real life are much the same.
I think. Sorry, David, to cut you off. Then you can finish. Sorry.
So I think you might as well use a simple method. There's an even simpler one than mine, actually, proposed by Berger and Selke. That gives it's a very simple calculation from the p-value, and that gives, I think, a false positive risk of 29% when you observe p equals 0.05. Mine gives 26%, so there's no essential difference between them. Doesn't matter which you use, really.
I guess James's point, the person who asked the question is called James. James gave an example of training people, so maybe he was touching on how do we teach people how to analyze their data and interpret it accurately. And I mentioned this, maybe I'm imposing my own interpretation on it, but it would connect nicely with a comment that was raised, which is more of a comment than a question. Reporting effect sizes and confidence intervals alongside p-values has been shown to improve interpretation in teaching contexts. And I wonder whether in your own experience, whether you have found that this helps as well, or whether you can suggest any ways to help educators, teachers, lecturers to help the sort of next generation of researchers properly use, because they're going to be around for a while.
Yeah, it's fine. I mean, you should have always report the observed effect size and confidence limits for it, but be aware that confidence limits tell you exactly the same thing as p-values, and therefore are very suspect. There's a simple one-to-one correspondence between p-values and confidence limits, and therefore if you use the criterion that the confidence limits exclude zero difference to judge whether there's a real effect, you're making exactly the same mistake as if you use p equals less than 0.05 to make the judgment. So they should be given for sure because they're sort of familiar, but you do need separately some sort of rough estimate of the false positive risk too, I think.
So James has another question. So he says, I'm struggling a bit with the P equals intuition. So how do you decide the band around 0.047 to use for the simulations? Presumably the results are very sensitive to this band. And if you are using an exact p-value in a calculation rather than a simulation, the probability of exactly that p-value to many decimal places will presumably become infinitely small. Any clarification would be appreciated.
Yes, that's not too difficult to deal with. You've got to use a band which is wide enough to get a decent number in. But the result is not at all sensitive to that. If you make it wider, you'll get larger numbers, but the result will be much the same. And in fact, that's only a problem if you do it by simulation. If you do it by exact calculation, it's easier. I've got a spare slide I can show if you want that illustrates that. To do 100,000 t-tests with my R script in simulation, it takes about 3 minutes on my laptop. So you can do an awful lot of simulations very quickly. I actually did a few with 1 million just to check on the answer. It takes about 30 minutes, which is not that long to wait. But it doesn't depend at all critically on the length, the width of the interval. And in any case, it's not necessary to do simulations. You can do the exact calculation. Perhaps I will show the.
So I'll just quickly add, this might be irrelevant now, but James did do a follow-up. So somebody else posted this in response to James's comment, which is, even if an exact calculation can't be done, it probably can, you can get a better approximation by doing more simulations and using narrower and narrower bands around 0.047.
Yes, that's absolutely true. Yes,
yeah,
I did check it with 1 million or occasionally. Yeah. I'll just show the slide, the exact calculation, which is not you see that now?
I'll just send it live. Yeah, we want to go to the back. Yeah,
this is how you do it, the exact calculation. This is the value of students T along the bottom and probability density up the side. The blue line is the distribution you get under the null hypothesis with a mean of 0 and a standard deviation of 1 in this case. So the red areas are the rejection areas for a t-test. The green curve is the t distribution. It's actually a non-central t distribution, which is what you need in this case. For the alternative hypothesis, which is so it's centered around here, and the yellow area is the power, and this area is 1 minus the power, 22%. So if you are calculating by the p less than method, you use the areas on this. 0.78 on 0.05 comes to 15.6, and that gives you a likelihood ratio of 15.6. They oops, what's happened then? They consider all values out in the red area or in the yellow area as being positives. The P equals hypothesis, what you want is not the areas, oh bugger, but the ordinates here, the probability densities, the probability of getting a t value of 0.04. Under the null hypothesis is that intercept, and under the alternative hypothesis that one. So for the P equals hypothesis, the likelihood ratio would be y1 on 2y0, 2 because of the nature. And that gives you a likelihood ratio of 2.8, and that corresponds to an FPR 50 of 26%, as we explained. Now, it's true that technically speaking, probability is a narrow band around y0 and y1. The probability of getting both those exactly would be 0, but the ratio of the two is perfectly well defined. It's not infinitesimal. In fact, it's 2.8. So you can, by calculation, get the same result as you get from simulation. I hope that was reasonably clear, but it may not have been if you aren't familiar with looking at those sorts of things.
No, I'm pretty sure it was very helpful, David. Thank you for doing that. So we have a few more questions. One by Martin Dominic, and he asks, what would be a meaningful recipe for choosing between alternative interpretations?
Alternative interpretations of what? Yeah,
I'm not sure. I don't know if Martin, if you're still there, if you could just clarify your question, but I guess I don't know. We can leave that one hanging and we can move on to the next one. So we have one question here. To calculate FBR 50, which I guess is false positive risk 50, I need to assume an effect size. Which one do you use in the calculations? Would it make sense to calculate FBR 50 for a range of effect sizes?
Well, yes, if you use the web calculator, for example, or equivalently, if you use the R scripts that are provided, then you want to specify what the normalized effect size is. And you can use your observed one. If you're trying to interpret real data, you've got an estimated effect size. It's true, this was shown in the 2014 simulations of the 2017 exact calculations, that likelihood ratio I gave of 2.8 when you observe p equals 0.05, that is done using the true effect size. All you've got is the effective, the observed effect size. So they're not the same, of course. But you can easily show with simulations that if you use the observed effect size in place of the true effect size, which you don't generally know, then that likelihood ratio goes up from about 2.8 to 3.6 from memory. So it's about 3 either way. You can just plug your observed normalized effect size into the calculator and you won't be led far astray.
Right, so Martin has got back in touch. So he says, consider hypothesis H1 versus H2. Which is the interpretation to go with?
Well, I'm not quite clear still what the two interpretations he's alluding to are, but I shouldn't rely on the p-value interpretation, that's all I can say. And you can do a full Bayesian analysis, some forms of Bayesian analysis can give results that are quite similar to the p-values. That can't possibly be generally true because they make quite different assumptions. Stephen Sen produced an example where they were essentially, there was no problem with the p-value, but that was for a one-sided test with a fairly bizarre prior distribution. In general, in Bayes, you specify a prior distribution of effect sizes, what you believe before the experiment. Now, unless you have empirical data for what that distribution is, it would be very rare, then I just can't see the justification for that. It's bad enough making up the probability that there's a real effect compared with there being no real effect, but to make a whole distribution just seems to me a bit like fantasy. Mine is simpler because by considering a point null hypothesis and a point alternative hypothesis, what in general would be called Bayes factors become likelihood ratios, and likelihood ratios are much easier to understand than Bayes factors because they just give you the relative probability of observing your data under two different hypotheses, and so it's not this is a special case of Bayes theorem. But as I mentioned, any hypothesis which any approach to Bayes theorem which assumes the point null hypothesis gives pretty similar answers, so it doesn't really matter which you use. In fact, there was an edition of the American Statistician last year which had 44 different contributions, I think, about the world beyond p equals 0.05. And I find it a pretty disappointing edition, apart from my own paper and one other, actually, because A, there was no agreement among people, and B, a lot of people didn't get round to making any recommendation. They said what was wrong, but didn't say what you should do in response. The one paper that I did like was the one by James Berger and Selke, because they recommended their false positive risk estimate, as I would call it. They called it something different, but that's what it amounted to. And that's even simpler to calculate than mine. It's a little more pessimistic. It can be slightly bigger false positive risk for a given p-value, but it's apart from that detail, their recommendations are much the same as mine. And it doesn't really matter which you choose.
Wonderful. Well, thank you for that answer there, David. So we have another one, which is if people want a procedure that does not too often lead them to draw wrong conclusions, is it fine if they use a p-value?
No, that maximizes your wrong conclusions among the available methods. The whole point is that the false positive risk is a lot bigger than the p-value under almost all circumstances. People refer to this as p-value exaggerating the evidence, but of course it only does so if you incorrectly interpret the p-value as being the probability that you're wrong, and which it certainly is not.
I think we've exhausted the questions on the Q&A, but I have a few questions, and it's really just to know your thoughts on so there's lots of recommendations about practical alternatives to p-values, and most notably the Nature piece that was published last year, I believe, where was it something like 400 signatories said that we should retire the p-value, and their alternative was to just report well, I think it wasn't their only alternative, but they recommended just reporting effect sizes and confidence intervals. Now, you're, as you've said, you're not against anything that should be standard practice, but I wonder whether this alternative is actually useful to retire the p-value. So that's my sort of first question. And the other question is to tinker with the alpha level, which has been popular in light of the replication crisis, to make it even a more difficult test pass when testing your hypothesis. So you can answer both or one, I don't mind. I'm just interested to know your thoughts.
No, I can answer both of those. I don't think the 400 author thing in Nature recommended ditching p-values at all. It recommended ditching the 0.05 threshold and just stating a p-value. That would mean abandoning the terms statistically significant, which is so shockingly misleading for the reasons I've been talking about. But he didn't say that you shouldn't give p-values, I don't think. And I don't think it really recommended an alternative. I would be against not giving p-values because it's the p-value that enables you to calculate the equivalent false positive risk, which would be much harder work if people didn't give the p-value. Also, of course, if you use the false positive risk, you'll inevitably get a larger false negative rate. And so if you're using it to make a decision, other things come into it than the false positive risk and the p-value, namely the cost of missing an effect which is real and the cost of getting a false positive. They both matter, and if you can estimate the costs associated with either of them, then you can draw some sort of optimal conclusion. But that's usually there aren't costs. Certainly the costs of getting false positives are rather low for most people. In fact, they may be a great advantage to your career to publish a lot of false positives. Unfortunately, this is the problem that the RIOT Science Club is dealing with, I guess.
Well, yes, yes. So apologies for the sort of woolly question about the retiring statistical significance rather than the p-value. The second part of the question was changing the alpha level. So some people have said that it should be 0.005 should be alpha threshold.
Yes, Daniel Benjamin said that, and a lot of other authors. I wrote to them about that, and they said, well, they didn't really think it was very satisfactory, but it would be better than the present practice. They regarded it as a sort of interim thing. Mm-hmm. And it's true that you would have fewer false positives if you did that, but it's a very crude way of treating the false positive risk problem, I think. I would much prefer to make a direct estimate, even though it's rough, of the false positive risk, rather than just crudely reducing to p equals 0.005. After all, if you have I do have a long paragraph in one of the papers discussing this particular thing, and if, for example, you're testing a hypothesis about teleportation or mind reading or homeopathy, then you probably wouldn't be willing to give a prior of 50% to that being right before the experiment, in which case 0.005 would be, you have to have a much lower p-value than that to get the false positive risk down.
Wonderful. Okay, well those are my questions exhausted. Now the Q&A message board has gone quiet, so I guess I don't think I'm unsafe in assuming that I think we've got a lot of happy attendees. There's no more questions for clarification or anything like that. So in that case, I think I will begin just wrapping up. So first of all, thank you very much, David, for your time and going past the hour as well. I will just put up a slide just to remind people about so we have, of course, our YouTube channel where you can see all of the recordings from the previous RIOT talks, and David's talk will be uploaded soon after we've finished this session. As I've put in the Q&A message board, you can see a link to David's website, Interpretable Science, which is a must-go-to website to learn all things about what David has talked about and more. And also, whoopsie-daisy, you can also see a list of upcoming talks in this slide here. And next week we are very excited to not only have Florian give a talk on the 5 selfish reasons to work reproducibly, but it's also going to be the inaugural talk for the University of Exeter RIOT Science Club. So please do join us next week for that. So until then, thank you all very much for coming, and yes, see you next week. Have a good weekend.
Thank you.